Let's take a look at another example here. I want to find the line integral of the constant vector field f equals I plus j along the path from 1, 1 to 5, 7. But I'm going to specify exactly what this path is here. Let's go ahead and take a look at this vector field real quick. This vector field is constant for every xy in the plane. The vector is 1 in the positive direction of x, 1 in the positive direction of y. That's everywhere. And then, of course, here I'm going to label this as being my point 1, 1. And up here is going to be my point 5, 7. But I'm not going there directly. Rather, I'm going to come to this point first. X is 5, 1. So the path I want is here. There's my orientation. And then from there, I need to come up to here. And of course, there's my orientation. So already I'm thinking of this as being curve 1, this particular line segment, and curve 2, this other line segment. Of course, I should label this as x and y. Okay, so I'm going to break this down in different pieces. For C1, I want to take a look at the integral over C1 of f dot dr. Now, f is going to be 1, 1. But what's dr? I want to actually try to work with this form. And it's not always very easy to do. Well, delta Ri is simply equal to delta xi, because I'm moving along the x-axis here. So that means that f dot dr equals 1, 1 dot delta x 0, which is just, whoops, delta x. So this integral will simply be the integral from 1 to 5 of delta x, which is simply dx, which equals x evaluated from 1 to 5, which is, of course, 4. Now this next piece I'm going to take a look at for C2. Delta Ri is simply going to be equal to delta yj. So f dot dr is going to equal 1, 1 dot 0 delta y, which is of course just delta y. So then this will give me the integral from 1 to 7 of dy, which equals y evaluated from 1 to 7, which is 6. So when I combine these, I'll get 4 plus 6, which equals 10. Now, finding dr like this can be extremely complicated. Both the only times I don't want to just jump right into it as such, maybe when I'm dealing with these line segments that's very nice like this. So let's take a look at yet another approach. So with C1, notice that R of t, I'm going to parameterize this line segment, is going to be 1 minus t times 1, 1 plus t times 5, 1, which gives me 1 plus 4t and 1. So this integral is going to be from 0 to 1, because t goes from 0 to 1, of f dot r prime of t dt, which equals the integral from 0 to 1 of 1 dot 1 plus 4t 1, which is going to be the integral. Oops, I need my dt. Oops, that's not what I want there. I forgot my r prime. It's supposed to be r prime, and I put r in there. So if this is r prime of t is going to be 4, 0. So that's going to be dot 4, 0 dt, which is the integral from 0, 1 of 4 dt, which is 4t evaluated from 0 to 1, which is just 4, which is what we'd expect. You know, that's the same thing we got last time. And we are integrating over that same line segment. So now for C2, I'm going to parameterize r of t. Again, 1 minus t. And now I have the point 5, 1 plus t times, and the point I'm going to is 5, 7. So this is going to give me the vector equation 1 plus 6t. That means that r prime of t, take the derivative, remember last time I forgot and then suddenly realized it, is going to be 0, 6. So I'm going to take a look at the integral from 0 to 1 of f dot r prime of t dt, which is the integral from 0 to 1 of 1 dot 0, 6 dt, which is the integral from 0 to 1 of 6 dt, which is 6t from 0 to 1, which is 6. And as you expect, again, 6 plus 4 equals 10. But what if I change the rules a little bit, and suppose I take a direct route? Suppose I go from here directly to here. Well, let's go ahead and parameterize that line segment again. So now I'm going to have r of t is going to equal 1 minus t times, see that first point is 1, 1, plus t times, and I'm going to 5, 7. And that's going to give me 1 plus 4t, 1 plus 6t. Of course, because the way I set this up, I didn't say it earlier. Actually, I think I did. I didn't write it. For t goes from 0 to 1. So r prime of t is going to equal 4, 6. So what I need is the integral from 0 to 1 of f dot r prime of t dt. That's the integral from 0 to 1 of 1 dot 4, 6 dt. That's the integral from 0 to 1 of 10 dt, which is 10t from 0 to 1, which is equal to 10, which is the exact same thing I had up here and all the other ones. Now, a previous example we looked at, when we took a different path, we got a different value. This one, we got the same value. So there are situations where the path is very much, or the value of the line integral is very much path dependent, and there are times when the value of the line integral is very much path independent. And that's the idea of conservative vector fields, which we'll talk about in the very near future.